Welcome back to the second climate modeling tutorial. In the last tutorial, we ended on a greenhouse model of Earth, learning how Earth loses energy to space and incorporating the effects of greenhouse gases in the atmosphere into our model via the transmissivity coefficient tau. In this tutorial, we will discuss the other side of energy balance, how Earth gains energy. The sun is the primary energy source for Earth. However, Earth is very far away from the sun, and the sun is much, much bigger than Earth. Although the sun initially radiates energy in all directions, because of the great distance between the sun and Earth, Earth takes up only a very small angular width in the sky, and thus by the time solar radiation reaches Earth, it's assumed to be traveling along the line that adjoins the center of the sun and the center of Earth. This is called the parallel beam approximation. Additionally, the radius of the sun and Earth are very small compared to the distance between them. This allows us to neglect the curvature of Earth, and the solar radiation is assumed to intercept a circular cross-section that has the same radius as Earth. If we then take the flux of solar radiation and multiply it by this area of the circle, we achieve the total radiation seen by the top of the atmosphere. However, Earth does not perfectly absorb all radiation that makes it here, and some of this energy is reflected off pale surfaces. The parameter that accounts for this reflection is called the Planetary Albedo, and some examples of highly dynamic and reflective surfaces include clouds in the atmosphere, as well as ice and snow in the high latitudes. We can take this albedo into account by subtracting the total off of the incoming solar radiation, and the result is radiation that's absorbed somewhere in the Earth system, and it's fittingly called the absorbed shortwave radiation. Piecing this all together, we just described how Earth receives energy from the sun, but for terrestrial planets, we know that this energy gain must be balanced by some energy loss, which we already discussed in the last tutorial. We'll refine this a bit more here though, because unlike the sun's energy, which we assume passes through a disk, Earth loses energy over its entire surface area. If we approximate Earth as a sphere and multiply the surface area of this sphere by the total energy given by the modified Stefan-Boltzmann law from the first tutorial, we can set this equal to the absorbed shortwave radiation covered in the last slide and simplify algebraically a bit to define energy balance for Earth. We note here that the energy in is the absorbed shortwave radiation, and that's set equal to the energy out, which is the outgoing long-wave radiation. When these two are exactly equal, the system is said to be in equilibrium, and the temperature at which this occurs is called the equilibrium temperature. When there are perturbations in either solar radiation or, for example, a composition of the atmosphere, anything really that would affect the absorbed shortwave radiation or outgoing long-wave radiation, it will lead to an energy imbalance, and the system is going to adjust until a new equilibrium temperature is reached. This will be the primary focus of the next tutorial.